Kennesaw State when I was an 8th grader. And my research projects mainly focus on trying to help people in different situations. So at Kennesaw State, I did research in predicting the car accident before it happens using the surveillance cameras that we have on major intersections. So I did that by looking at car movements and how drivers tend to drive with larger vehicles and smaller vehicles. Right now at NASA, I'm working on analyzing the astronaut's brain while they're doing multiple processes. For example, if they're flying the aircraft and they have to do they have to pull a safety mechanism in the aircraft. Those are two very difficult tasks to do simultaneously. How we can better suit those astronauts to have them under less stress in those situations.
Pardon me. I was wondering, are you using Emery's technique for doing direct wire to synapse, or are you doing something exterior to the cranium?
So actually, I'm not quite sure on what they're using to get that information from the astronauts, but what I am being given is data on what type of stress levels they were under which.
Oh, I see. So it's not, okay,
yeah.
Gotcha.
So what we'll be discussing is, first I'll be giving you a general definition of what data science is, and then we're going to be talking about how data science is extremely multidisciplinary. So there are a lot of different subsections that you must understand well in order to do data science. And then there are a lot of commonly misused phrases that there are in data science, like big data, what's the idea of big data, and words like that, like deep learning. And then we're going to learn our respective jargon. So in order to sound smart in your work environment, you have to be able to talk the right words and use the right phrases in the right context. And then finally, how you can get started in data science. So there's a lot of stuff that you can do in data science, but the best thing to do is start now before everybody knows data science, and it's just a big competition. Third level. So the three main kind of areas of knowledge of data science is computer science / IT, so information technology, math and statistics, and domains and business knowledge. So knowing your computer science is extremely important because there are different languages like Python, R, and SAS that you should be familiar with, at least one of those three, in order to understand how to write your programs efficiently. Next is math and statistics. There's different tests that you have to do as a data scientist in order to analyze your data. The correct, I want to say like, steps showing that the algorithm works on a large scale. You can't put that on a larger scale than your testing. So why should you learn data science now? First of all, it's the future. There are a lot of companies like Amazon, Facebook, Google that are using data science on a large scale to track each individual user and see what type of user they end up being. So for example, if you shop on Amazon a lot and you're into shoes, Amazon will be able to they'll be able to recommend you different types of shoes as you're browsing the internet. On the right side, you might see like some advertisements from Amazon or something like that. They're able to track your user data from when you were on their website. So number 2 is discovery. So as a researcher, I'm given a lot of data, but if I didn't know data science, it would just look like a bunch of words to me, right? But data science allows me to be able to recognize, the parts that the pieces of data that users seem to be struggling with, and how I can improve those struggling points to make the user experience better. And number 3 is in demand. So data science is a really hot topic of discussion right now. There's a lot of branches of computer science, but data science is one that's known to be extremely difficult. But since it's difficult, the people that know data science really well are always being offered jobs and positions in large companies like Facebook, Google, Amazon, etc. And number 4 is you're able to tame your data. So you're able to understand what the data you're looking at actually means. So that could be like, out there like MySQL and something like that, where you're able to learn how to create your database, how to manage your data for a free price.
Is there one you recommend for data science type things like Postgres or MySQL or?
I would recommend MySQL because it's free and it's based off the SQL language, so you'll be able to get that knowledge and skill set for free.
That's just the way you use when you do your research?
Yeah.
MySQL, okay.
MySQL. And the last thing is you should be able to work with unstructured data. So a database is structured data, right? So you have a certain number of columns, you have a certain number of rows, and usually those columns or rows are filled out completely. But if you're given unstructured data like an image or a video, and you're trying to look for an object inside of a video, that's unstructured data, right? The video can be absolutely anything. Information is changing a lot inside of unstructured data. All right, so now we're going to move on to how data science is extremely multidisciplinary. So here you'll see, let's focus on the right diagram. You'll see that there are 9 kind of subsets to data science, right? There's artificial intelligence, predictive modeling, pattern recognition, machine learning, statistics, operational research, data analysis, computer science, and business intelligence. So those are the 9 kind of things you should be somewhat comfortable with in order to excel in data science. And I'll be giving a quick breakdown of each one of those, so you can look those up later in your free time. All right, so the first one is statistics. So I have 3 main points that you should be comfortable with statistics, and those would be distributions, density, and theorems and algorithms. So looking at distributions, there are 3 main distributions. There's a binomial distribution, a geometric distribution, and a Poisson distribution. So in a binomial distribution, that's where we are trying to find the number of successes in a given amount of trials. So that could be something like trying to see how many 6s we can roll if we roll the dice 12 times, right? So there, the notation is bin, in parentheses, n comma p, where n is the number of successes and p is the probability. So in our case, if we're trying to roll the dice 12 times, we're trying to get 6. The probability of getting a 6 is 1/6, right? Because there's 6 different numbers on a dice, 1, 2, 3, 4, 5, 6. And we're trying to get the number 6, so that's a 1 out of 6 probability of happening. Next is a geometric distribution. So that's where we're trying to find the number of failures we have until we get a success. So that could be, going back to our dice example, the number of non-6s we roll until we roll a 6. So here we have a different variable called k, which is looking for the number of attempts that we have. And the formula for this is, P equals P times 1 minus P to the k power. I don't know, that didn't show up too well, but the lowercase p is representing the probability in your testing environment. So in our case, that would be 1/6. And that's the same right here. And we're going to the kth power where k equals 12. So our final probability will be where we're multiplying 1/6 by 5/6 to the 12th power. And what that value represents is the probability of not getting a 6 at all in those 12 experiments. And if we take 1 minus this, then we would get the probability of getting a 6 in our 12 cases. And the last one that I want to talk about is a Poisson distribution. And what a Poisson distribution is essentially a binomial distribution taken on a larger scale where the number of attempts that we have goes to infinity while the probability goes towards 0. So an example of this could be, let's say I wanted to find if I knew that the number of 911 calls for firefighters is 8 calls per week, and I want to find the probability of having 11 calls in that week. I would use this formula. P equals a to the k power over Okay, so in this formula, what I have is that A is the lowercase p that we had before. So I'll just use lowercase p. And K is the number of attempts that we have. And E is the natural log, so that's just the 2.7 repeated. And then A again is the probability of that happening. So if I was to calculate the example out of having, of trying to get 11 firefighter calls instead of the 8, which is the normal one, it would come out to something like 0.072, which is the probability of having those 11 calls. Does that make sense? Okay, great. So the next thing that I want to go over is theorems and algorithms. So under theorems, I have Bayes' theorem, central limit theorem, and the law of large numbers. So we'll first start off with the Bayes' theorem. So Bayes' theorem is essentially conditional probability, right? And since there's 3 of each, they both have a 0.5 chance of happening. But if I was to say that 2 of these spheres were black, and 1 of the cubes were black, and the others were white, I could then go on to an even more elaborate plan where this 0.5 is distributed into the spheres, where black has a probability of happening 0.67 times, and a non-black has a probability of happening 0.33 times, because it's 2 over 3 and 1 over 3. And then with our cubes, we have the probability of black being 0.33, because we only have 1, and then this being non-black having 0.67. So that's the Bayes' theorem. It's conditional probability essentially. And next we're going to talk about the central limit theorem. Yes.
Is Bayes' theorem a precursor to performing chi-squares analysis? It looks like it's breaking down, like regardless of which one you're focusing on, it's breaking everything down into how it distributes. And that chi-squares analysis is trying to figure out intelligently how to group those.
Right.
As what's significant. Is this because I've heard the term Bayes' theorem before, but I haven't really looked into it. It looks like this is kind of like a precursor to that. Is that used with chi-square analysis?
It is. Later on in statistics, we use chi-square analysis to see we add up all the possible outcomes in chi-squared. So this is kind of a lead on into that.
Oh, okay.
That makes sense.
Looks like, thank you.
So next we're going to talk about the central limit theorem. And what the central limit theorem basically says is that as the number of, as our sample size increases, we have a normal distribution. We can assume a normal distribution. So when we say normal distribution, we mean that sample size of above 30. So if I'm trying to test the number of people for some experiment, the number of people that I should be testing should be above 30 for me to assume that the distribution is approximately normal and the graph will look just like this. So if the graph looks just like this, I'm able to use more functions such as z functions and t functions, which are a little more higher level statistics. Yes?
That number 30, I hear that a lot from statisticians. Is that an actual part of the central limit theorem, or where does that come from?
So the number 30 is just a kind of base level number that most statisticians use to assume that the central limit theorem applies to their problem. So we have to assume that after we get a 30 sample size, that the distribution will look like this. But if we don't get a sample size of 30, it could be whatever distribution possible.
Data is useless until you get 30, right?
Right, exactly. And then the next thing is
What if it's not normally distributed there? What if it's positively or negatively skewed?
So if it's positively or negatively skewed, so something like this where it's skewed left, we're giving more people, we're increasing the sample size. Does that answer the question?
It's okay.
Yeah? Okay. So next is the law of large numbers. And what the law of large numbers says is as we increase our sample size, it becomes closer to the real population statistics. So if the population of my study was 1 million people, And I can't sample all those 1 million people. If I'm able to sample, let's say, 10,000 people, the statistics that generate from that 10,000 is much closer to the 1 million than if I was to sample, let's say, 100 people or 1,000 people. The larger the sample size gets to the actual population, the closer the statistics are to the population. All right, so the next thing that we're going to talk about are algorithms. So the two important algorithms that I have noted down are k-nearest neighbor algorithm, or the K&N algorithm, and random forest. So what the K&N algorithm is if we have a group of data, if we have groups of data scattered along a plot, so if we had something like this, somewhat random data, but we're able to see that there's three main parts to this data, right? We can distribute it down 2 lines and make three different groups, right? We're able to have class 1 being the leftmost, class 2 having the middle, and class 3 being the rightmost. So that's what the k-nearest neighbor algorithm is. It's where we're grouping data based off their relative location on a graph. Okay? And the next type of algorithm that we have is the random forest algorithm. So that's where we're creating tree diagrams for each different possible output that we can have, and then we're finding the mode of that output. So for example, I have a diagram in the bottom right, which is showing that there are 3 possible outcomes. There are 3 different tree diagrams, and 2 of those tree diagrams have an output of class B, and 1 of those has an output of class A. So since class B is the mode, or like the most occurring outcome, our final class, or like what we could say is the majority, would be class B, because there's more outcomes of class B than class A. Okay, so here's some more statistics terms that should be a little comfortable with. Those are linear regressions, classification, subset selection, dimension reduction, nonlinear models, and tree-based methods. So if you were to take an introduction to statistics class, or maybe the class after an introduction to statistics class, you'll be able to learn all of this, but they're a little more complex than what we've gone over so far. So I'm not going to touch on that too much. All right, so the next branch of data science that I want to talk about is pattern recognition. And pattern recognition is a branch of machine learning in which we're looking for patterns inside of our data. So we can have 3 different variables: discrete variables, continuous variables, and discrete binary variables. And a discrete variable is where if we were to take an interval of negative infinity to positive infinity, some of those numbers don't exist. So if I was to have a interval of
2 million, but 2,000,000.2 doesn't exist.
correct.
Okay.
Yeah. So that would be a discrete variable, or discrete variable. So a continuous variable is basically the opposite, where negative infinity exists, or all values from negative infinity to positive infinity exist, so there's no missing out on anything. And then discrete binary variables is where if we were to convert something to binary, that those numbers don't exist in binary, but they may exist in our real life world. So those numbers that I wrote before, -5, 3, and 207, these numbers might exist in our normal lives, but in binary those numbers don't exist. And these numbers are just random. I just said those. And one way we can represent pattern recognition is through representational vectors, which is what we'll talk about next. So let's say I had a study in which I had ball, soccer ball, and a weighted baseball. So I have the data, the rough data estimated for each one of those balls, where in red I have the weight of the ball in grams, and then in blue I have the diameter of the ball. So for example, a tennis ball weighs 58 grams and has a diameter of 6.5 centimeters. I can represent that tennis ball by saying 58 comma 6.5, the x value being the weight and the y value being the diameter. And I want you to look at the data for a second and see if you recognize anything that looks a little weird.
The weight of baseball seems really heavy.
Yeah, the weight of baseball seems a little weird. Okay, so here's the graphical representation. If you were to put this on a graph where the x-intercept is your weight and the y-intercept is your diameter, and the red line right here is the line of best fit that the computer generated. So what this basically means that in the beginning, we can see that we're kind of close to the line of best fit. Our points are pretty close, but towards the end, in the 2000s, they don't really seem to be matching up very closely to our line of best fit. And I think this distribution seems linear, but if you don't agree with me, I also put up the graphs for the power and the quadratic. If you just don't think that it should be linear, I put a power and quadratic. But the main thing that I see is that there's a big outlier right here. A ball that weighs 2,500 grams and has a diameter of 9 centimeters, and that was the weighted baseball. So using vector representation, we can assign different classes to each of those balls, right? So I put the tennis ball was in class 1, so was the yoga ball, the basketball, and the soccer ball, but I put weighted baseballs in class 2. So class 1, class 1 is basically saying as the mass increases, the diameter increases. The R value shows us our correlation between diameter and mass. So it has a correlation of 0.9959, which is pretty close to 1, and 1 is basically saying that there's a complete correlation with mass and diameter. So, yeah.
So in class 2, like if you had like I don't know, I can't think of a smaller ball, but something made out of like a heavier material like tungsten, would that fit in class 2?
Yeah, that would be class 2.
Okay.
So an example could be the weighted baseball, or something like a balloon, right? A large balloon that has a big diameter, but it weighs very little. That's an example of class 2. And I also put the different types of graphs if you thought it was a power or quadratic distribution.
What tool are you using to draw the charts and do the analysis here?
That was a Python program that I made,
Okay.
where I just put in the points and then it gives me the graph.
Okay.
Is there a, I guess what we call a correct distribution, not distribution, geometry of best fit for this data, or is there another 2D data best fit?
The correct distribution would be kind of up to you how you want to interpret it, but I think most people would agree that it's a linear distribution, as we say that the mass increases and so with the diameter. So it's pretty linear in my opinion. But if you think it could be quadratic, and a quadratic distribution would be where as the mass increases, so does the diameter initially, but eventually at a certain point, as the mass increases more, the diameter goes down. So it doesn't seem to be quite quadratic, it's more linear. Okay, so applied pattern recognition. So pattern recognition is literally everywhere. So that could be image processing, computer vision, seismic analysis, speech recognition, and fingerprint recognition. So an example could be like our phones. Most of our phones have fingerprint scanners to unlock our phone. So what those fingerprint scanners do is when you're registering your finger, they take kind of like pictures of your finger and they track where your lines in the fingers are. And next time you put your finger on the fingerprint sensor, it's matching up where those vectors are from the initial fingerprint scanning to where the vectors are now. And if they're in the relative safe position, it'll unlock your phone. Okay, so artificial intelligence is linked to data science, but not completely. It's linked to data science through something that we call machine learning. So what artificial intelligence is it's like giving technology the mindset that humans have. So for example, IBM Watson is a really good artificial intelligence, piece of artificial intelligence that is used on a large scale. So giving robots the power of brains is the idea of artificial intelligence. But machine learning is using past data and using our data science skills to predict what outcome could happen if based off past data, if you sold more product, what's it called? The amount of money you make back increases. So if we were able to use that data and implement that in a larger scale, using machine learning, you'd be able to see how much profit you could possibly make. So this is just a refresher on machine learning. I'm not going to go too much into machine learning, but I'll talk about like very basics. I'm going to use an example of spam email. The list would go on and on of what all possible spam emails you could receive. So what the machine learning algorithm does is that we have this kind of equation: learning equals representation plus evaluate plus optimize. So when we talk about representation, that could mean something like the naive Bayes model, for example, is an idea of representation. So representing our data in I'll write that down because that's actually important. So the naive Bayes classifier is basically looking for keywords in our spam emails. And once it sees those spam emails, it makes a judgment of whether or not it should be spam or not. So, for example, using enhancement, or I'll use Nigerian prints. Using Nigerian prints, if it sees Nigerian prints, it thinks of different possibilities of what all that email could contain without reading it. Because if it was reading it, then that would be extremely inefficient and a very inefficient way of solving it. So if it sees Nigerian prints through the Bayes classifier, it evaluates that and decides whether or not spam or not spam. So again, that comes back to our Bayes model of conditional probability. So if it sees Nigerian prints, I think we could give it like a 0.7 probability of sending it straight to spam and a 0.3 probability of not sending it straight to spam. And then based off that spam, it's able to detect whether it should be, there's a second process that it goes through. When it sends it to spam, it reads the email again and makes sure that there's a good chance that it's not supposed to be in your inbox. And that probability is usually 0.99 compared to 0.01. And with this is so it basically goes through 2 rounds of analysis to finally declare that it should be under spam and not spam. And usually if it goes to spam on the first time, it'll go straight to spam. It very rarely goes to this 0.01 figure. So next, yes?
I was just wondering, so when you have spam and then they say you don't think it is spam, does that change the model? Or?
It does. It does change the model. So If someone was to actually send you an email saying Nigerian friends and it goes straight to spam, what you do is you'd say, yes, it should be in my inbox, and that goes back to the naive Bayes classifier, basically saying that if you see something different in this email, such as like the font text is normal, or the email contains regular words, not anything bad, nothing, no explicit content or anything, then it should go straight to your email. And another thing that it does is it records the sender of the email, and every time that person sends you an email using that email address, it'll go straight to your inbox. Yes.
So it sounds like it's taking all these factors, like the location of the sender, the email of the sender, different features of the sender's email, like what their email looks like.
Yeah.
And it sounds like it's taking an action and then waiting to see whether or not that action was correct in the eyes of the user, and then using that to twist those, like that 0.7 value, that 0.3 value. It sounds almost like the machine equivalent of a hunch.
Can you define hunch?
Like
Ready, fire,
yeah, almost like that. Just waiting for either the user doesn't put up a fuss, like and everything's working fine, in which case it reinforces its current model, or the user says this is not spam or this is spam, and the machine says, oh, I was wrong, and what do we call it, back propagation?
Yeah.
When it takes those and throws them back through that same decision tree to change the.
Yeah, that's basically what it's doing throughout the entire thing.
So
yeah.
So well, yeah.
Okay. Great. So that was the number one thing that we should be aware of about machine learning. And number two is generalization matters. So there's a lot of, if you were given a lot of data, there's always going to be an exception somewhere, right? So if you were given a million sets of data, maybe 1,000 of that set is a rare exception, but we can't make rare exceptions for every single possible case. So we have to think on a more major level of thinking. And if we were to say a Nigerian prince, a 0.7 probability is pretty high, isn't enough. So if you were to create the perfect machine learning algorithm that's able to send your spam email straight to spam or straight to your inbox, just having that data isn't enough. You have to be able to write up exactly how that data works and how the machine learning algorithm works in order for it to be classified or considered as a proper working algorithm. You have to explain how it works. Number 4, intuition fails in high dimensions. So yes.
I'm sorry, can you go back to 3 for just a moment? How that data is related to itself, how the different attributes of it interact so that it can do a proper job. Is there a language? Is there certain metadata that's used? I'm completely unfamiliar.
Yeah, so how the machine learning algorithm works is that
now, how you represent it to the, when you say the data alone is enough, you have to tell it how, it's the telling of it. I'm wondering how that's done.
So that's called training data, where we first give the machine learning algorithm a certain amount of data, and then we let it process that information, and then we throw more information at it to make sure it knows it. But if it doesn't know it, then we throw the special cases at it, right? So for example, an enhancement might not necessarily need to be in spam, and if we saw that over and over again, the machine learning algorithm keeps putting it inside of spam, we can direct it to be, instead of spam, always send it to the inbox.
Right, but how would you let it know that it's specifically the word enhancement? In other words, I understand about consider, but telling it how to consider it, that's the thing that intrigued me, what you said.
Number 3, when I said data alone isn't enough, I wasn't talking, it's not, when I meant data alone isn't enough, I meant when you're talking to someone in real life, you can't just give them this machine learning algorithm and expect them to know what that means, even if you have a lot of comments.
Yeah, still, it is kind of interesting to see how the machine is going to figure out that enhancement is or is not the problematic word it thinks it is.
Right.
So to train it that enhancements of training data that says enhancement or productivityenhancement.com is not a spam email address, and just feed that to it several
That's
times.
exactly what you
Just
do.
capture.
Yeah, that's exactly what you do. And and sometimes it wouldn't. So that's what the yes, it should be in spam, or no, it shouldn't be in spam. That's what that's for me. Okay, intuition fails in high dimensions. So we think in a very three-dimensional world where, like, if I was bringing this mouse up, or like this water bottle, you would know that it would be a cylinder, because we think in a three-dimensional world. But the problem is that computers do not think in a three-dimensional world, they think in an infinite dimensional world. So we have to think of how the computer is able to put a matrix inside of a matrix inside of a matrix. So for example, one of the sets of data that I have for NASA has 6 dimensions to it. It's a matrix inside of a matrix. Yeah. I think that's enough. So the very innermost section in this piece of data is the only part of data that I should be looking at, right? So if I was to put this in table form, you would see that X, Y, or X, Y. This table right here demonstrates the innermost matrix. But this table in actuality is in a very larger matrix, which is the outer one. And it keeps growing larger and larger until we get to the outermost. So in our 3D world, we think of at the biggest possible point, we can have a 2D matrix. But in real life, it could be, in the computer world, in data science, it could be infinite dimensions. Okay, so number 5 is saying that more data is better than a smarter algorithm. So if you're able to feed your algorithm more data, it's able to learn better than if you were to have less data and you fed that data to a very smart algorithm. It wouldn't perform as well as a mediocre algorithm with a lot of data, because that mediocre algorithm knows just about every possible case.
So the algorithm is only as good as the data that's being put in it?
Yeah, so if you have more, it's always better to have more data, right? The algorithm can always be tweaked whenever, but getting that data is extremely important to be able to train your algorithm to work better, to work more efficiently.
So like you talked about with the 30 and the central limit theorem, you hear Google say things like, after 18 months we forget everything, but in that 18-month span they try to store as much as possible.
Yeah.
Are there any rules of thumb as far as it's sort of the information age, or like how much data you would consider to be good or an ideal case?
So it's very different for each type of case. For example, like Google, they would throw out their data every 18 months because, user data changes every single year, we could say. Like one year I might be into clothes, or the next year I might be into technology. So being able to distinguish every user individually is important, but that's more towards Google, right? If I was Snapchat or Instagram, I would be able to see how the user has been able to upload their data and what kind of messages they've been sending over a period of time. So I would need all of that data from when the user started Instagram to currently.
And what do you, like we say with traffic accidents, what would you consider to be a good history of data?
Just about, I would say actually for the past 2 years,
2 years.
since we've gotten more technology inside of our cars that help us with, traffic accidents, like stopping the car when it sees a car in front of you or something like that, that has gotten more popularity in the past 2 years than we would have had in the past 5 years, if that makes sense, because more safety regulations have been taken. So there are many different machine learning models, and it's good to be familiar with a few of them. So a few examples are binary classification, regression classification, and multi-class classification. Those are just 3 general ones. I won't go too far into detail about each one of those, because it's very dense data. But I would suggest knowing at least 2 models in machine learning. All right, and number 7 is correlation does not imply causation. So I have this little cartoon over here which says that this guy took a statistics class and now he thinks he'll do, the girl says that he thinks the guy will do better because he took a statistics class. But just because he took a statistics class doesn't cause him to know statistics, if that makes sense. There's definitely a correlation of taking a statistics class and knowing statistics, but there's not necessarily causation, if that makes sense.
Is there a way to prove causation or how?
Unless you're able to prove it in the real world, like for example, if I throw this water bottle, it will land. That could be the only way you can show that causation does exist. But in the computer world, you can't necessarily show that causation or correlation has something to do with causation. It's very hard to prove that in computers. Okay, so next is predictive modeling. So in predictive modeling, this is mostly used in startup companies because the difference between predictive modeling and data science is that predictive modeling is going very far in depth into how the user interacted with the system, right? So for example, if I was a startup and I was trying to see how my 200 users use my system, I'll be extracting gigabytes and gigabytes of information from that user in order to see, in general, how do users use my system. But if I was Facebook or Instagram, I have millions and millions and millions of users. I can't possibly have gigabytes of information for each one of those users. I can surely have megabytes or kilobytes of information for each user, but it doesn't make sense to have gigabytes of information for each user. So predictive modeling is data mining on a very small scale, but very dense data mining. And it's a branch of machine learning. Okay, so next is business intelligence. So business intelligence is basically like the old school data science, where if you are into business intelligence, it's very easy to switch to data science. But the difference between business intelligence and data science is that business intelligence is working with structured data and only structured data, while data science is working with both structured and unstructured, right? So that means that business intelligence is working with databases and different types of structured data, while data science can work with structured data as well as unstructured data, which could be pictures, videos, stuff like that. Okay, so knowing computer science is extremely important in order to be a data scientist, right? So knowing an object-oriented programming language and knowing most of the libraries pertaining to that language is really important. So for example, knowing your libraries in Python, Java, or C++, knowing an object-oriented language like those 3 is extremely important. But if you don't know a programming language yet, I highly recommend you learn Python, because Python can also be used for data science. So the way that I would see someone learning data science, if they're brand new to computer science in general, is to first learn Python and how Python works, the syntax behind Python, how the compiler understands what we write, and then switching into data science. And all data science is for Python is just more libraries being used.
I have a question.
Yeah.
Functional programming, does that play a big part in data science?
Functional programming? Of course.
So, Scala is a big functional programming. So, would Scala be something that you should look at as far as going forward? Because that's a growing language, and that's my understanding. Data science and a lot of functional programming is a part of that. So, where does that? How does Scala fit into the course computer science skills? Is it something that could possibly I don't know, with these, is it just seen as another language tool to add to the skill set, or something that could maybe surpass that? I don't.
So Scala is a very, in my opinion, difficult language to learn compared to the 3 that I have on the board, which are more object-oriented and C-based. But if you are already into computer science, it's great to know Scala, it's great to know R, it's great to know SAS, different data science tools you can use. But as to start off with, knowing one of these three languages would be better. But if you already know computer science, it's great to know Scala as well.
Speaking of SAS, is there a free version that, or something to get people hooked on crap?
I know that SAS is extremely expensive. It's extremely expensive. It's like $10,000, right?
To get started.
Yeah. But I know for college students, they get it for free. There's a SAS program like SAS for universities or something like that, where they can get it for free, but not the full version. But yeah, SAS is extremely hard to get your hands
What
on.
about non-college students? If you don't know if they have any kind of a limited edition or anything like that for.
I don't think so. No.
Thanks.
Maybe discounted, but not free.
If you're gonna deploy something similar to that question at a really large scale to use machine learning and computer vision and data science, what would be your stack of choice so you don't run into these licensing costs and that type of thing?
So there are 4 different types of programming languages you can use for data science. Those would be Python, R, SAS, and Scala.
Right, but like R and SAS are pretty unrealistic to deploy because of the money involved.
Right. So
I'm sorry,
if-
I thought R was free.
Yeah,
Oh, okay.
yeah, R is free.
Okay.
R is free. So if money was a problem, I would say to learn Python because Python is very versatile, right? So you can make different types of programs in Python, not just data science, but also, more towards machine learning, not related to data science, but more machine learning or different types of web apps with Python. So if money was an issue and you really want to learn data science, I would say Python's the best.
No, not learning, I mean like, say you wanna put, cameras and servers on every intersection so you can monitor for traffic accidents. How would you build that stack of technology?
So the best example I could give for that is at Georgia Tech, I'm doing research where we're putting supercomputers on drones and then we're flying those drones out to natural disaster areas. We're looking for victims. So I'm not sure how they did it in the traffic accident one because I wasn't on site for that one. It was more of a remote location. But I do know for the natural disaster one, all of the processing is happening on site and not coming back to Georgia Tech in order for us to analyze it. Okay. Okay, yeah. Data analysis. So data analysis is like kind of the baby version of data science, which is working more with databases and less with statistical knowledge. So data analysis could be something as basic as, looking at stock market values and seeing, okay, the stock for this company is going to go up. But with data analysis, it's less of using statistics and more of using predefined data and finding patterns through that. So if you were a data analysis, the best thing to do to get into data science is learning something like Python or R or SAS, and also learning more of statistics, because the main difference is that data scientists know more statistics than data analysts. Statistics, machine learning, and pattern recognition. Operational research is basically just making sure that you know what's going on in your research study or something like that. But I want to get on to some of the commonly misused words. So when I say big data, I don't mean like in the middle of middle data and extremely large data, because I once heard someone say that big data is in between middle data and extremely large data. But what big data really means is that it's so much memory, it's so much information, so much data that you can't possibly have all that data on one workbench. You have on one workstation. You have to have multiple CPUs. You have to have multiple. You have to have a lot of RAM, a lot of gigabyte space on your hard drive in order to work with big data. So it's just basically like large, ginormous amount of data. All right, so number 2 is the cloud. And cloud computing, I know at Atlanta Code Camp there's a lot of talks on cloud computing. But when we talk about cloud computing, we mean instead of wasting a lot of money on buying a physical machine like this, having a Linux-based machine in the cloud, doing all of our work for us and just giving us the output is a more efficient way of, spending our money. Yeah.
No, good.
Oh, okay. So this is used a lot in startups because they need to process all their user data, but they don't want to spend thousands and thousands of dollars on machines. So it's little investment in hardware, more investment in software. So number 3 is deep neural networks. So deep neural networks allow for supervised, unsupervised, and semi-supervised learning. And I'm going to get a little more into deep learning and deep neural networks in a second. But it's just, deep neural networks are actually used for supervised, unsupervised, and semi-supervised learning. And number 4 is data analytics. And data analytics is basically analyzing past data in a linear fashion, right? So Google uses this a lot. I'm sure you've heard of Google Analytics, which is basically looking at past search results for, let's say, your company, and how you're able to use that past search results and better and put your more relevant information higher up on Google.com. Okay, so here's some important jargon that we're going to go over really quickly. So we're going to learn about classification, regression, clustering, decision tree, neural networks, deep learning, reinforcement learning, database, and data mining. So number 1 is classification, and that's coming back to classification is coming back to how we classify our data, right? So that could be our class 1, class 2 example values with the balls, where one is a linear approach and the other is more of a logarithmic approach. So it's just how we classify our data, because if we were given a lot of data, there's different types of possible ways we would classify it, such as class 1, class 2, or we could just have it all together and have a really weird distribution where our line of best fit didn't really go through all of our points. Okay, so next is regression. So regression is how far off our predicted value is from our true value. So looking back at the ball model, we had 1 ball here, 2 balls here, 1 here, and 1 here, and our line of best fit was something like that, if I remember correctly. And what the regression is how far this point is from its predicted value right here. So if the mass was 2,500, 2,500, and the diameter, predicted diameter was, let's say, about 30, and the actual value is all the way up here, which was about 65, the regression for that would be 30, which is just the difference between the actual minus the predicted. And that goes back to linear regression. And that's one statistics term that's used a lot, linear regression and isotopic regression and different types of regressions. All right, so next is clustering. And clustering is where we, kind of like classification, where we're grouping our data based off their relative position, or not their relative position, based on where they are on the graph, right? So that goes back to our k-nearest neighbor algorithm and our k-means cluster. So what k-means cluster does is it takes a set of data, the number of clusters that the user wants. So let's say I want 3 clusters. The program is going to randomly put 3 different points on your graph, and whatever points are near it or are closest to this mean are going to be in that cluster. So it's similar to k nearest neighbor, but the main difference here is that these points are going to be random. So if I was to redo this test, the circles will probably be in different locations.
I have a question. What a sample data for like clustering to like geocodes, like if you look at certain geocodes and don't know, a state or something like that, as opposed to
Yeah.
a different state.
Yeah. Okay, so next is decision trees. And decision trees are going back to when we talked about random forest. And in random forest, we talked about how the input would be all of the possible different decision trees, such as this is the decision tree, of an outcome, and taking the mode of those decision trees would be our random forest. So what a decision tree is, it basically shows all the possible outcomes of a sample. Okay, so neural networks. Neural networks work a lot like our human brain. So what they do is they take something like, let's say we wanted to be able to identify the difference between a car and a bus. Right, so we wanted to be able to detect the difference between these two. Well, first of all, we needed to try and teach it what a bus looks like and what a car looks like, right? So that would be our input. Our input would be pictures of buses. Our hidden layer would be dissecting this bus into its geometric form, right? So a bus is, if we look at this, I could see probably 3 different ways to look at a bus and be able to tell it's a bus, right? So first of all is its wheels, right? So by looking at its wheels, we know that it's a vehicle, right? It's a vehicle if it has wheels. We could just assume that. Next I see is this big rectangle right here. So the difference between a car is that it doesn't really have a big rectangle. So if I saw this rectangle, I could classify this as a bus. But if the program was still confused on whether or not it should be a bus or not, it should be looking at this section right here, this kind of Z-looking shape. If it sees that Z-looking shape, it should automatically classify it as a bus because a car can never have like a Z shape, if that makes sense. So that would be the hidden layer, and then the output would be bus or car. So that's a neural network, and a deep learning. Deep learning is basically just this, this put on a larger scale, right? So an example I have is a face recognition algorithm I wrote. I'll put that. Okay, so this program is now looking for faces, and it sees my face. So it classifies me as my name, Apaar. Then I put a picture of Bill Gates up there, and it's able to recognize that that was Bill Gates. That's basically what deep learning is.
Are you using like Darkflow or any kind of framework?
I'm using TensorFlow.
TensorFlow.
TensorFlow. Yeah. All right. Okay. So next is data mining. So data mining is basically data science, but the main difference is it's more of examining the data through patterns. It's more of pattern recognition, whereas data science is both pattern recognition and past data. Being able to tie those two together is the difference between data science and data mining. So you use data mining in data science, yeah.
So for actual data mining, is it necessary to do data analysis to figure out which pattern you're going to use, because data mining isn't going to choose the pattern for you, correct?
Right.
Okay.
So the kind of way of thinking would be data analysis, then mining, and then data science. Okay, so next is reinforcement learning. In reinforcement learning, we want to be able to reward the system if it gets something correct, right? So what that means is if it is able to recognize that this was a bus, it should be told that it is right, so it knows that the output that it gave is correct, so it's able to, next time it sees a picture of a bus, it's more easily able to identify that it's a bus. So in the right, I have a picture of kind of the mindset behind how a reinforcement learning kind of algorithm would work. So it goes from the environment, it goes from the agent to the environment, and if the environment is correct, it gets the reward, and if it's wrong, then it goes back to the agent and learns why it was wrong.
Is an example of a spam system?
Yeah,
where the user-
yeah.
Would the user be the agent or the environment?
The user would be the environment. So if he says it's correct, then it gets the reward, and wrong. So next is database. It basically just stores all of our data, and we're able to write to it and read from it and basically analyze our data in that database. Okay, so some important libraries to know, this is just limited to Python. I know we're a little short on time. Is NumPy, SciPy, Pandas, Matplotlib, Keras, TensorFlow, and PyTorch. And what the first three are is strictly for data science. So NumPy would be more of our algorithm, or keeping our data local to the program. SciPy would be more of keeping our words in the program. Pandas would be keeping temporary data structures, and Matplotlib would be graphing our possible outcomes. So that's how I created those graphs earlier. I used Matplotlib. Keras, TensorFlow, and PyTorch are all used for deep learning. So that's what I used to create this right here. I use TensorFlow and Keras. So yeah, those are usually used for deep learning.
You find yourself using anything but Python with the research?
I just use Python, that other language I'm most comfortable with. So the way that I see getting started is by using a website service kind of like Pluralsight or Udacity to learn the basics of Python, if you're interested in Python, that is. To learn Python first, see how the language works, see the syntax, because the syntax for Python is extremely important. If your syntax is wrong, the compiler won't do anything about it. And once you're comfortable with Python, take a data science course on Python. That will teach you those libraries that I just talked about. So yeah, are there any questions? Yeah.
Any recommended, I really like what you presented here. Are there any recommended books or other resources to get deeper into the subject that you would recommend for beginners?
There's a book that I have in my room, I forgot what it's called, but it was by the For Dummies kind of company, like Python for Dummies. It was a really good book, but the place that I learned the most was Pluralsight. So if you're unfamiliar with Pluralsight, it's more of like a Netflix.
I'm an
It's like Netflix for coding, basically. Yeah, that's where I would recommend learning. That's where I learned the most. Yes.
Would you be able to share the slides?
Yeah, sure. I think Atlanta Code Camp does that on their website. Yes.
For most of us, folks who like more IT-based skills, as far as learning the business and math logic, what would be some sources to learn that as far as getting into data science?
For statistics mainly, I would say take a course from edX, EDX. So what edX is basically a bunch of online colleges. Like there's Harvard, there's Georgia Tech, there's MIT, there's a bunch of different colleges that can teach you a wide range of skill sets. So yeah, I would say take a class from edX. They're generally free.
Oh, yes.
edX, yeah, EDX. Yes.
I'd like to ask some more about the, let's go back to this, to the spam email example.
Okay.
And the AI processes behind that. So you mentioned that with the training data, you present to the AI all correct data as its foundation on which it begins to make decisions.
Right.
And adjusts itself from there over time. Now, let's say that some user wants to be in trouble.
Okay.
And tells the spam filter, all emails from Nigerian prints are not spam, and just does that over and over and over again. The spam filter will, if I'm not mistaken, learn that Nigerian prints emails are never spam. It will never send them to the spam folder after being told that a number of times. Now Google anonymously pulls people's spam filter data to improve its global training network, or the training data that it uses. Isn't that a vulnerability? Where if enough people decide to just tank their local training data, that the global system at large can be affected, then no one will be the wiser since most.
There would have to be a very, very large scale of people saying that Nigerian prints should be microbox in order to make a difference. So just having one or two people, or even like 1,000 people saying that Nigerian prints should be microbox, that won't really do too much.
Organization company creates a zombie nest
That's
with
what
a
we're
few
gonna-
100,000 machines to trick Google into thinking that some search term is okay.
That's gonna be big business, I think.
I'm thinking of like the new
And it's not
super large scale
Is it?
DDoS attacks that can assume control of certain services.
I'm sure at a certain point, Google will be able to see that, you know, there are a lot of users for some reason saying Nigerian prints should be microbox, that they'll just completely shut down the idea of Nigerian prints being able to in your spam or your inbox and just send it straight to spam. I'm sure at a certain point, something like that would occur.
Which I suggest you go to.